Ladies and gentlemen, good morning. I'm Camilla Ronchei, and before starting my presentation, I would like to thank my co-authors from the University of Parma and also the Italian Ministry of University and Research for the financial support according to the PRINE grant. The present work deals with the proposal of an analytical methodology for the fatigue assessment of notched components made of additively manufactured metals subjected to multi-axial cyclic loading. Such a methodology is based on the application of the multi-axial fatigue criterion proposed by the research group of Carpentieri and Vantadori and the Taylor's point method. The novelty lies in the identification of the critical point where the criterion is applied through the formulation of a novel critical distance, departing from the conventional alpha LADAD intrinsic crack length originally proposed by Professor Taylor for conventional metals. My presentation consists of the following section: a brief introduction related to the fatigue behavior of additively manufactured metallic components, then the formulation of the novel critical distance, the definition of the critical plane orientation, together with the assessment of fatigue strength and life, and finally some conclusions. As is well known, additive manufacturing is characterized by many advantages with respect to the traditional manufacturing techniques. For example, it allows the realization of customized structural components with the complex geometries, and a considerable low material waste is produced by additive manufacturing. However, AM components still face several open challenges related to the uncertainties in their structural performance, especially under complex cyclic loading typical of in-service condition. AM components, in fact, are particularly susceptible to fatigue-related damage due to their typical high surface roughness and the presence of internal discontinuities. They serve, as a matter of fact, as a stress concentrator, which promote early crack formation, thus causing a shortening of the high cycle fatigue life. Moreover, these detrimental effects become even more severe in the presence of notches or other geometric discontinuities, which further amplify the local stress fields. In particular, the combined effect of intrinsic AM defects and geometric discontinuities in a component subjected to multi-axial loading conditions results in highly complex multi-axial stress state with multiple competing crack initiation planes influenced by both the orientation and the interaction of the principal stress directions. Nowadays, therefore, the goal of the research in the AM field is still to find and validate advanced criteria for the fatigue assessment in order to more exploit the use of such a powerful manufacturing technique. In this regard, it has been found in the literature that criteria based on the critical plane represents a valid tool for the fatigue assessment of AM metals. In this context, the present work proposes an analytical methodology representing a first attempt to estimate the fatigue strength and life of notched components made of AM metals under multi-axial, medium, and high cycle fatigue conditions. The main steps of the proposed methodology are here summarized. First, some input data need to be defined. Then, the novel critical distance is developed. The critical point PCR is identified at a distance equal to half of the critical distance RAM. At this point, the stress field is computed through the formulation proposed in the past by Lazzarina and co-workers. Then, at this point, the critical plane orientation is determined and the fatigue assessment is performed according to the multi-axial fatigue criterion by Carpentieri et al. Now, let me emphasize the innovative aspects of this work: the formulation of the critical distance and the identification of the critical point where the criterion is applied. In particular, although the main concepts of the point method are here adopted, the critical distance adopted to locate the critical point differs from the conventional value of the L-alpha LADAD intrinsic crack length, originally proposed by Taylor as previously said. In particular, the relationship for the critical distance RAM here developed is given by the present equation, where R1 and R3 represent the characteristic length of control volume for respectively mode 1 and mode 3 loading computed according to the straight energy density approach. The critical distance also depends on lambda, the Biaxial iteration, defined as the ratio between the applied shear stress amplitude and the applied axial stress amplitude, the ratio between the fatigue strength of notched specimens under mode 3 and mode 1 loading, and also function of some surface roughness measurements. Now we can focus our attention to this first term of the equation of the critical distance, and in particular, it can be observed that in case of poor mode 1 loading, this term tends to the control volume characteristic length for mode 1 loading, R1, whereas in case of poor mode 3 loading, this term equals the characteristic length of the control volume for mode 3 loading, R3. Moreover, lambda in this term is divided by the ratio between the fatigue strength of notched component. And it can be observed that for the same applied stresses, when the notched fatigue strength in mode 1 is lower than that in mode 3, the first term of RAM becomes more similar to R1. And analogously, when tau 3 AN is lower than sigma 1 AN, this first term approaches the characteristic length of the control volume for mode 3 loading. In order to compute the characteristic length of the control volume under mode 1 and mode 3 loading, we adopted the strain energy density approach. And in particular, for V-notched specimens, R1 and R3 are given by these two equations. And it can be observed that among several parameters, they depend on the fatigue strength of smooth specimens under mode 1 and mode 3 loading, evaluated at a number of loading cycles equal to NA. Note that closed form expression for these characteristic lengths are only available for sharp notches, and therefore for other local geometries such as U-notched specimens, numerical simulations have to be performed. As just said, the characteristic length of the control volume depends on the fatigue strength of smooth specimens. And in this work, these fatigue strengths are evaluated as a function of the defect size present in the AM component, following an approach similar to the well-known one proposed by Murakami for conventional manufactured components. In particular, by using the model proposed by Alves and co-workers for AM titanium alloy specimens, the fatigue strength of smooth specimens for mode 1 loading at a number of loading cycles equal to 1 million and under fully reversed loading condition is given by this equation, where the square root of area max represents the square root of the expected maximum defect size in terms of area. In order to compute this area, a defect content analysis has to be performed by means of a statistical method based on the well-known extreme value theory proposed in the past by Murakami. An analogous relationship should be used also for the fatigue strength of smooth specimens for mode 3 loading, that is delta tau 3A. Moreover, the critical distance RAM, as already said, depends on a term accounting for the surface roughness, that is RT and RV represents the total height of the roughness profile, and the maximum roughness profile valley depth, respectively, as here depicted. The idea of including surface roughness relative parameter in the critical distance computation originates from a research performed by Ronchei and co-workers, where the roughness profile was assimilated to natural micronotches. Once the critical distance is defined, the critical point PCR is identified at a distance equal to half of RIM, from the notch root along the notch bisector. Knowing the stress field at this point allows, of course, the computation of the principal stresses, sigma 1, sigma 2, sigma 3, together with the corresponding principal stress direction 1, 2, 3, identified by the principal Euler angle, phi, theta, and c. Since the direction of the principal stress axes are generally time varying over time in case of multi-axial cyclic loading, since the direction of the principal stress axes are generally time varying in case of multi-axial cyclic loading, their average direction have to be taken into account. In particular, by using the weight function here reported, the average direction of the principal stress axis coincide with the instantaneous ones at the time instant 1, the maximum principal stress sigma 1 attains its peak value over a loading cycle. The orientation of the critical plane, that is the verification plane for the fatigue assessment, is then defined by taking an off-angle delta in the average plane 1 with cap, 3 with cap. In particular, rotating counterclockwise the average direction 1 with cap by the off-angle delta, we obtain the normal to the critical plane, that is W. The expression of the off-angle delta is given by the present equation, and in particular, this angle is equal to 0 when the two fatigue strengths are equals, and therefore, the normal to the critical plane coincide with the average direction 1 with cap. Moreover, this angle can reach a maximum of 45 degrees, which occurs when the fatigue strength of smooth specimen under mode 3 loading equals that under mode 1 loading divided by the square root of 3. Finally, according to the present criterion, the normal to the final fatigue fracture plane, which is the one experimentally observed post-mortem, is assumed to be coincident with the average direction 1 with cap. Knowing the critical plane passing through the critical point PCR, then we can consider a local frame, UVW, and the stress vector SW can be decomposed into a normal stress vector N, orthogonal to the critical plane, and a shear stress vector line on such a plane. Unlike the normal stress vector, the amplitude of the shear stress vector is not uniquely defined, since the time-varying direction of such a vector, which describes a closed path during a loading cycle. Therefore, the maximum rectangular pool method proposed some years ago by Araujo and co-workers is here adopted in order to compute the amplitude of vector C. The fatigue endurance condition is then expressed by setting an equivalent uniaxial stress amplitude, sigma AQA, equals to the fatigue strength of smooth specimens under mode 1 loading. And finally, the fatigue life NCAL is computed in terms of number of loading cycles to failure by solving the equation reported on the bottom through an iterative procedure. And now we can move to the conclusions. In the present paper, a preliminary analytical methodology has been proposed for the fatigue assessment of additively manufactured notched components subjected to multi-axial loading in the medium and high cycle fatigue regime. Such a methodology is based on the joint application of a multi-axial fatigue criterion and the point method proposed by Professor Taylor. The novelty lies in the identification of the critical point where the criterion is applied through the formulation of a novel critical distance, which depends on several factors. That is, the characteristic length of the control volume derived from the said approach, which are able to account for the defect size. The ratio between the fatigue strength of notched specimens under mode 3 and mode 1 loading, the axiality ratio lambda, and the surface roughness. In conclusion, such a methodology, in order to demonstrate its potential, has to be validated, of course, through an extensive experimental campaign, considering different types of notches and also loading conditions. Such a validation will be presented in the next talk by my colleague, Andrea. Thank you for your kind attention.